We need to ask ourselves on when to do what is if the data is categorical or if it's numerical. Now, if the data is categorical, that does mean no matter what else is true, this is going to be some version of a chi-square test. Now, if it's categorical, the next question you need to ask yourself is how many variables does it have? Does it have one variable, one population? Or does it have two variables? And I guess what we could do technically is we could say that is two or more variables.
What does that say?
Excuse me, could the following homerooms report to the theater for pictures? Burn.
Now, if it's one variable, what we're going to have is it's going to be some kind of chi-square goodness of fit test. And there's two different flavors of the chi-square goodness of fit. One flavor of the chi-square goodness of fit is where the null hypothesis is that the proportions are equal. The other flavor of the chi-square goodness of fit is where your null hypothesis is that the proportions match the given values. Now, really, in this case, it's the same chi-square test whether or not you're testing to see if the proportions are equal or the proportions match the given values. The only difference is that sometimes I've seen students get confused because they're like, well, it just said I was equally likely to get hearts, diamonds, clubs, spades. It didn't give me a set of proportions test. Well, if you're equally likely to get one of four different things, that means your expected proportion would be 0.25 for each of them. Or if you were checking are student absence is equally likely to occur on any given day of the week. In other words, your proportion for each day of the week would be 0.2 because 20% for each of the 5 school days. So it's the same idea, but just sometimes they will not give you a list of proportions because if they say they're equal, you just have to divide to figure out what the list of proportions is. So just be aware of that situation turning up. The next thing is if there's two or more variables, that's going to put you in a different style of chi-square test. One thing you might be doing if it's two or more variables, the question you need to ask yourself is it one population or is it two or more populations? If it's one population, what you're going to be looking at is a chi-square test of independence. And your chi-square test of independence, see if I can get some kind of dividing line there. Yeah. Chi-square test of independence, what that is going to be is that's going to be the one where your null hypothesis is just that that the variables are independent. Just to separate them. So that's going to be your null hypothesis. If it's two or more proportions, that's going to be your chi-square test of homogeneity. Now, the chi-square test of homogeneity, its null hypothesis is going to be that the proportions are the same, are equal for different populations. So, so you have equal proportions for different populations. Mechanically, and this is important to consider, mechanically these two tests are exactly the same. There is no mechanical difference between a chi-square test of independence and a chi-square test of homogeneity. The only difference that you have is in how the samples were selected. And if you do them in your calculator, you're going to put your table in as a matrix both times. You're going to do chi-square tests both times. There is not a mechanical difference. The difference is just in how you set up your null and alternate hypothesis. For example, if I wanted to find out if Playing sports affected how much time students spend on homework. What I could do is I could take a random sample of 100 South Caldwell juniors and seniors. And I could ask them two questions. I could say, do you play a school sport? Which is a yes or no categorical answer. And then I could say, do you spend at least, let's say 3 hours a week doing homework outside of school? And that would be a yes or no question. So I have two categorical responses, but what I have is a single population. I have a single random sample that I ask them two questions to. That means it's a chi-square test of independence. And I'm checking to see if their answer to the first question, do you play a sport, affects their answer to the second question, do you spend at least 3 hours outside of school doing homework a week? Okay. On the second thing, I could do a very similar thing, similar study, but I could randomly select 50 juniors and seniors who were student athletes. Then I could randomly select 50 juniors and seniors who were not student athletes. And I could compare, and then I could ask both of those groups the question, how much time do you spend at least 3 hours a week outside of school doing homework? And what I could do is I could compare the response rate for the student athletes and the non-student athletes. That would be a chi-square test of homogeneity. Do you see how I did it almost the same way? The only difference is in the test of independence, I did a single sample with two questions. And on this one, I did two separate samples asking both groups the same set of questions.
What's the advantage of one or the other?
I would say if you actually have a list of who's a student athlete and who's not a student athlete, you would probably be able to get more accurate results with a smaller sample size, setting it up like the homogeneity. But the reason you do a test of independence or not is you don't, a lot of times, is you don't always, that might not be an easy list to come back. Or in some cases you might not know, like if you were asking questions about, favorite color and favorite food. You can't just look at somebody and say, hey, I know what your favorite color is. I'm going to put you in the blue group or whatever. Okay.
What's the one where it's...
If it happens to be numerical, there's two big subgroups you have. You have the group that is proportions, and you have the group that is means. So your two big subgroups are proportions and means. If it's proportions, we definitely care how many variables or proportions I have. So if it's proportions, one thing you need to know is proportion is always going to be some version of a z-test, and if you're using it in a calculator, be sure that you choose the option that is z for proportions. Don't be deceived by that one that does not say for proportions. So it's always a z-test if it's proportions. Just like if it's categorical, it's always chi-square. Now, under proportions, you have the one that is for one population, and you have the one that is for two populations. Now, the reason I say one population, two populations is do not be deceived. If you know that 40% of America approves of Trump and 60% of America does not approve of Trump, that is not two populations. You have asked one group of people one question that had a yes or no answer. Therefore, that is just a one proportion z-test. So what you're testing for usually with this one proportion z-test actually, the technical name for that is the large sample z-test for one proportion. I guess I should write it in the technical way. The large sample
Should have made the first tree bigger.
z-test. I'm doing the best I can for one proportion. And then your null hypothesis for that will basically be that your population proportion P equals some decimal value. Occasionally they'll use a fraction, but it's usually some decimal value. And your alternate could be that it's either not equal to, greater than, or less than that value. Now, Once again, if you only are asking one question, one group of people, that's a one proportion. If you have this one for two populations, that is, I'm going to abbreviate here, is a large sample z-test for the difference in proportions. We could say that they're population proportions. Usually your null hypothesis for those is going to be that you have two population proportions whose difference equals some numerical value, usually not always zero. Any questions? Now, with this, a large sample z-test for difference in population proportions, a good example of that would be if I have, let's say I'm doing the Trump question, I have yes or no, do they like Trump? But instead of just asking nationwide, I ask people in Oklahoma and people in California. And I want to know if Californians and Okies have different opinions on President Trump. Probably so. But basically what I have there is I have two different proportions, one for Oklahomans, one for Californians. And I want yes or no, do they support Trump? And I'm comparing to see if there's a difference. Two different populations, two different samples. That's what makes it that. Now, side note, it is absolutely true. And if you feel like we're doing the same thing sometimes this can be done as a chi-square test of homogeneity. Because if you look at it, that little table we have a 2x2 table where we have basically two categorical variables. What state do you live in, and do you support Trump, yes or no? So, in this case, it could be done as a chi-square test of homogeneity. Generally, if it was just two proportions and it was a binomial yes-no situation, I would stick and do it as the large sample z-test for difference in proportions because I think that's easier. But if you see, hey, they threw in a third state, they not only have Oklahoma, California, they also have Virginia. Now, I cannot do it this way. I can't compare three proportions with this test, and that lets you know, oh, I have a larger set of proportions, so it's a test of homogeneity. Or if I just had two states, but instead of having, do you approve of Trump, yes, no, undecided, I can no longer do it as a z-test. I can do the percent who support Trump, if it's yes, no, undecided, the percent who are undecided, but I can't compare all three. So if you have more than three responses or more than three categories, that's going to throw you to a test of homogeneity, definitely.
So if you have 30 states, then you do chi-square?
When I'm dealing with means, it can be a z-test or a t-test. It's usually a t-test unless you know sigma, then it's z. So if you know sigma, it's a z-test, but it's usually t because you don't know sigma. Does that make sense? It's usually a t because you don't know the population standard deviation, but if you know sigma, then it's z. Any questions? Once you know you're testing for means, we need to care about how many populations I have. So do I have one? So if I have just a one population, or if I have two populations, let me write that where I have them. So if it's one population, that's going to be a just a t-test or a one sample t-test for means. So one sample t-test for population mean. Usually in that case, my null hypothesis is just going to be that my mean value equals some number. If I have two populations, it's important to make sure that these two populations are actually independent, because what I'm going to do is I'm going to do an independent two-sample t-test for the difference in population means. And usually your null hypothesis there is going to be that it's mu1 minus mu2.
Following homerooms, report to the theater.
You also have a situation where numerical. I also have the situation with numerical where it's paired. Now sometimes when it's paired, I'm working with means that are paired, and that's going to be, if I'm working with means that are paired, that's going to be my paired t-test. Your paired t-test is going to have a null hypothesis that is, ooh, that's ugly. It's going to have a null hypothesis of the mean difference equals some number. Now, once again, mechanically, this test is remarkably similar to this test. In fact, mechanically, it's identical. The only difference is, on this one, on the paired t-test, I started with pairs of data that I subtracted and found the differences, and I'm looking at the average differences. So that is my paired t-test. The last thing you can do with paired data, and I'm totally running out of room,
What's the difference in paired
is I can look at my slope. I need to find a place to put that.
Yeah, I don't know what you're doing right now, Mr. Hass.
I will try. So what we're going to do is we're going to have a slope. And when you're dealing with slope, that's your linear regression t-test. And that's usually with a hypothesis of my slope being equal to 0. Remember this, it can be for a slope that's not equal to 0, but when you're dealing with paired data, there's two different things you can test for. You can either test for the differences between them, or the mean difference. If I'm testing for the mean difference between those those ordered pairs, that means it's a linear regression t-test or a paired t-test. When I'm testing for the slope between them, that's the linear regression t. So when I'm dealing with the paired numerical data, the question is, do I care about the difference between those ordered pairs, how far apart x and y are, or do I care about the relationship between x and y, the slope of those? So if you care about the association, the relationship is for slope. If you care about the differences, it's the paired t.